Hello, everybody, and welcome to our meeting, Deep Learning Adventures. Joined by my co-hosts, George Zotto and Robert Craig. And tonight we're going to be continuing on a specialization from Coursera that we're studying called TensorFlow Data and Deployment, Data Pipelines and Deployment. If you're not familiar with our group, I'm just going to share the window of our meetup page in case you joined us from a different venue. Let me share my screen. All right. So we started probably a little more than a year ago, and we often cover courses that we encourage everybody to take and go through with us, as well as we do coding adventures and often interviews of some of the authors of either the software or the courses that we've taken. Right now we're taking TensorFlow's data and deployment, and we're into course 4, which is titled Advanced Deployment Scenarios with TensorFlow. And George will start us off tonight, followed by Robert. George will cover week 1 and Robert will cover week 2. Week 1 has to do a TensorFlow extended, or what they call TFX, which is sort of the larger ecosystem that covers all things TensorFlow. And I'll let George cover that. And then there is a really nice set of pre-trained models so that you can do work with those in what is known as TensorFlow Hub. And Robert's going to introduce us to that and how you would use TensorFlow Hub to do transfer learning. So we'll cover that as well tonight, hopefully. I'll go ahead and turn this over to George.
Perfect. Thank you, David. Thanks, everyone, for joining us. And as a reminder, many of the slides we're going to see today, they're put together by Deep Learning AI and Coursera. So I'll make sure that we attribute credit to them. Welcome, Elena.
Hello.
Hi. All right, let me share my screen. Feel free to admit anyone joining us. I'm not monitoring the participation list. Okay, share screen, entire screen. Cool. Can you see my screen?
Yes.
Yeah. Perfect. So this course 4 of the specialization, as David mentioned, is kind of independent of what we've seen so far. Again, we've developed and deployed models on Android devices, iOS devices, on our web browsers. We've done some interesting and advanced data pre-processing steps with pipelines. We've seen how to optimize our code with different caching and prefetching techniques and so forth, so that the GPU and CPU are as fully utilized as possible. This last course focuses on slightly different aspects of the TensorFlow ecosystem. And again, as a community, we're still discovering and exploring it. So we'll touch on one specific component of what is called the TensorFlow Extended Environment, which is a platform for deploying production scale machine learning models and pipelines in TensorFlow. I'll share this link with you online, but under tensorflow.org/tfx, you'll see this larger ecosystem or platform that TensorFlow supports. And briefly going to touch upon this guide that TensorFlow team has put together, just to give an idea of what it looks like. There's some really good visualizations here that I think explain the picture a little bit better. So this visualization here basically.
Make it a little larger for us, please.
Yeah, absolutely. Yep.
Thank you.
Thank you. So this visualization explores a little bit the different components that make up the TensorFlow extended pipeline. So you can have anything from training and evaluation data and how that passes through different different steps and different architecture components, to maybe looking at some statistics, maybe looking at some data validation, maybe transforming your data, as we've seen with TF data, to training models, to tuning your models, to evaluating it, to finally pushing it. And we will focus today a little bit on this week one, on this very last component called the pusher. And specifically, we've seen TensorFlow.js, we've seen TensorFlow Lite. We kind of touched upon TensorFlow Hub. Robert will cover that in detail, but I'll focus here on the TensorFlow serving, which is basically how do you take a model and how do you deploy it either locally or in a production setup, and how do you have an API that you or anybody you shared with can use to deploy. So if you work with maybe other architectures like for example like Amazon Web Services and SageMaker, there's an option there for you to deploy a model and you get an API back. This is similar to that if you come from like a cloud background. So again, there's so many components here. We're going to focus today on this pusher for deploying models on a serving infrastructure. And let me zoom in a little bit more. So on the slides as well, Lawrence mentioned this, but building the model itself, it's only part of the journey, right? You can build it locally, you can build it on Colab, you can build it on your cloud infrastructure, wherever you build it. That's a very small part of the machine learning journey. You still need to figure out when you deploy this in production, okay, how do you scale this? How does the data collection work? Any infrastructure you need to set up? What are the features? Any data manipulation or data verification you need to do? You need to monitor this whole infrastructure as well as your data quality, as well as your performance of your model, and as well as serve it so that different devices or different users can call your model and get responses back. So we're going to focus on this specific smaller component here. We're going to switch gears from modeling and data feature extraction, data pre-processing to actually serving on a production level environment. So as you've seen, the typical journey that we've taken is we first focus on the data, and we focus on the model, then we focus on the deployment part of it. So we start with ingestion, validation, transformation. We pick the appropriate model, depending if it's a classification or regression task. We analyze the performance of our model, then we want to deploy it somewhere so that we can use it. And we've seen deployment on edge devices like Android, iOS, as well as on our web servers. But the challenge here is that we are converting our models to a different format, TF.js, for example, or TF Lite, and then deploying it on our edge devices. And what happens if we have different versions of our models? Or what happens if we have a better, newer, more updated version of our model, and so forth? How do we update the different devices, and how do we make sure that everybody who's using our model is up to date and running the latest version? So let's say, for example, we have some kind of like weather prediction app or some kind of traffic prediction app, and we want to make sure that our Android, iOS users, as well as our web users, when they go to our website or app, they're getting the latest and most up-to-date results. So that's one thing. The other thing is, what if we wanted to scale our, let's say we notice that we have multiple users, right? We're talking about production level here. So we have thousands of users using our model, and want to make sure that we are scaling appropriately. So in this setup, we are leaving the compute resources up to the edge device. So if more users can join us, that's perfectly fine. They just need to download and use the app. But the other alternative would be if we have some kind of a central server here, and that is called model serving in this TFX paradigm, where basically we treat this as an application programming interface, as an API. And then you can have our apps pointing at here. You can have our desktop versions or our websites pointing at it, and they can make API requests. Our model, which is hosted somewhere on infrastructure, obviously, will take those requests, run our model, and reply back with a response. Again, the challenge is, as I mentioned before, if we have multiple clients, iOS, Android, or TF.js, and we want to push newer versions of them, they might be slightly out of date. That's why a better approach would be to have a central location where all these different clients can point to it, and then we can push newer versions of model. That's number one. Number two is if you want to add more infrastructure, let's say a newer GPU or more GPUs to our server, we can do that independently and without interfering with the clients. Or if you have maybe some kind of distributed architecture where you have multiple servers and we have some kind of load balancer that accepts requests, goes round robin on them, and replies back with the appropriate response. I found that very interesting. So there are a few things that we need to install to make this happen, and Lawrence mentioned this on his course as well. We'll be using Colab. There are different ways to do this, but we'll be using Colab. And in Colab, the virtual machine that's running on Colab is a Debian version, which is a Unix version of an operating system. And specifically, they use this package manager called Aptitude. So we'll use this to install our TensorFlow serving modules. The recommended way that Lawrence mentioned as well is using this Docker container, where you don't have to worry about prerequisites, requirements. Everything is packaged and prepared, ready for you. And the other thing that we will use extensively is we'll use this saved model format, that once we train a model, we need to save it to the saved model format that we can deploy it on our server. There's some extra links here. I can post them later, but I think the best way to look at this is just looking at a notebook. And I'll zoom in a little bit here. And we'll look at a very basic model. We're not going to focus on the model here. Again, we're going to focus on how do we deploy this on a server, either locally or somewhere on the cloud? How do we get an API? How do we call that API? And how do we get responses back from it? So let me connect actually. Cancel. I have another notebook open, so I'll just use the output of my previous running here. So what do we need? We need TensorFlow for sure. We need this JSON library. Let me zoom in a little bit more. That we will use for our input and output parsing. Again, this is API call, so JSON is basically how do we interact with other servers. A library called tempfile that will help us create temporary directories and temporary folders on our virtual machine here on Colab, as well as a requests method for calling HTTP post and HTTP get requests with remote servers. And most of our data usually they're wrapped around the NumPy array, so we're definitely going to use NumPy as well. So TensorFlow 2.5, that's the stable version that Colab is running. And then in terms of what packages do we need this, sorry, let me close this a little bit. The stable version of TensorFlow model server, and specifically Lawrence mentioned that there's a few precompiled versions that are specifically optimized for Windows and Unix as well as macOS versions, but we will use this what is called the universal version of it, which is basically a version that runs on most Unix-like operating systems. So we'll add that to our list of packages to install, and then we'll call this apt update so that we can install them. As you can see, it's installing those specific modules as well as any prerequisite that they need. Cool. So we downloaded them. Now we need to install them. So apt-get install. The name of the module is TensorFlow model server. That gets installed as well. It looks like it's running, yep, version 2.5.1. And then at this point, we just need data, model, and we need to save that model in the model save format. So Lawrence uses this very simple hello world, machine learning 101 example where you have an input of x's, line, and an input of a series of outputs y, and this is just a linear relationship between x and y. So x is our input and y is our output, and this is just a linear relationship between them. But our model doesn't know that. This could as well be a nonlinear relationship. So we'll build and train a simple, very basic model, a very basic DNN with just one dense unit here. Again, this is a linear model, so we're not going to introduce any nonlinearity with activation functions and so forth. So our model will expect a single input, a scalar, and it will do its calculations of weight and biases, and it will give us one specific output as well. We'll compile this using this stochastic gradient descent optimizer, and this is now a regression task. So we're going to use a mean squared error loss function. So we're not trying to classify a class here. We're trying to be as close as possible to the correct y relationship of y and x. This is obviously an overkill here with 500 epochs. We just want to make sure that our model learns that linear relationship between y and x pretty well. So we do that. Verbose 0, we don't want to see any progress. So that's what we're doing here. And then we finish training the model. Cool. Then what we can do in the end is we can test the model, right? We can do model.predict and give it a list of inputs. In this case, we're just giving it 1. And ideally, our model should be really close to the relationship of 2x minus 1. So 2x minus 1, where x is 10, would be 20 minus 1, 19. We're getting 18.9, something really close to 19. So nothing new here. We've seen this in the past. Something new here is maybe creating this temporary directory where using this temp file library, and we can create multiple versions of our model here and create our path. And if that path doesn't exist, we'll create it. Otherwise, we'll delete it and recreate it. And then we'll run this model.save on our export path under temp and save it in this TF save model format. So right now I'm saving it under temp 1. The version is 1. That's why it's saved there. And you'll see two things. You'll see this save model.pb and variables. And that variables contains all the weights and biases for our model. We can examine how this save model looks like using this bash command called save model CLI. We need to point it where our model path is, and maybe some flags to give us all the different attributes. And what we can see here is, I'll focus on what we are interested in. We are interested in what is called the signature definition and the name of it specifically. So when we save this model in that save model format, it has this structure internally, or the signature definition. We need this name, serving default, basically how we interact with our model. This is made up of inputs, as you can see here, dense input, and the shape is just a scalar, 1, as well as outputs. And the shape of it is, again, a simple scalar. The -1 doesn't mean anything. It just means that you can have multiple, a collection of them, basically. But we're interested in just this second argument here, which just basically tells us that we're going to give a number, we're going to get back a number. Some other specifications here, we're not interested in that. We're just interested in the name of the signature definition and what is the input-output parameters. Cool. A few more things we need before we set up our TensorFlow model server. We need what is called this REST API port. We need to know where our server will be listening for requests from the outside world. What is the model name? We can give it any name we want. And what is the model path? Where is that saved model? Where is that variables and model.pb that we saw above? So we have this model directory under temp. So far, we've been working in Python, but we'll be running this in a bash, which is basically a more native way to interact with operating system programming language. So somehow we need to tell our operating system that our model directory is now under /temp. So we do this in Python using this os_library.environment method. And we're basically exporting this environmental variable model there in our local host. Then how do we call this bash command? And this underscore or dash pg means run this as a background so that this is run independently, regardless if our session, collab session doesn't work. We run this TensorFlow model server, the module that we installed. We need to specify the API port. We can put any number we want. That is available, that is. We're just using 8501 here. Model name, this is just a string. We can give it any name we want. In this case, we're just calling it hello world. And the path is very important, where our model is. Again, it's under temp. Any output and so forth, any errors or output, store it under server.log. And this, with this no hop and background command, will run in the background in a separate thread. So basically now we have a server listening for requests under port 8501. And we can tail those logs and see what's happening. So there's some initialization going on here. We have save model, variables name, the weight and bias is basically updating models. And then what we're looking for is this exporting HTTP REST API under, in this case, it's localhost 8501. If you had this under production level or production server, this would be something else. It would be your URL, and probably you'd have some kind of authentication or access management in front of this so that your app and clients can authenticate. Cool, we're gonna need some testing data for this, and we'll use NumPy here, NumPy array to provide a list of, let me zoom a little bit more so we can see, a list of inputs. In this case, the format is a little bit interesting. It's a list of lists, and each list internally is an item. So this is how we, our model is expecting our input. So we'll do two inferences in parallel. Basically, we'll run our model with 9 as input. We're going to get one output. We run our model as 10 as input, and we're going to get another output. And the other thing we're going to need is, if you remember from our signature definition, we need to tell our TensorFlow server, we need to call it appropriately. So the way to do that is by defining the signature name, and the name of the definition that we saw above was serving default. And the data needs to be under this key called instances, and the data is our x's, our NumPy list here. Cool. So this is our data object. It's just a dictionary of key value pairs. Signature name is this, instances is this. The next thing we're going to do is, since we're making an API call, we need a headers, and we need to form our post request appropriately. So this is a JSON request we will be sending. So we need this headers object defined under content type. If you've done web development, you might know this. You can add other options here like XML or HTML or text or other versions. We're going to be using JSON here, and then this module request that we installed in the very beginning has a post method for us. We need that API name, and that API name or URL is wherever our server is running. In this case, is running localhost in our collab. That REST API port 8501. If you remember, we had a version number which we initialized to 1. This is the beauty of it. We can change it later. This is all these models, and then the name of our model. We hard-coded it as hello world, and this is, we want to call the predict method of our model. So let's digest it again. So let's visit wherever our TensorFlow model server is. We want the first version. Under models, we can have multiple models. We want the hello world model, and we want to call the predict method on that model. That's the API. We need our data, and our data is our x's, if you remember, our inputs 9 and 10, and our headers. We need to specify that this is a JSON object. So we do a post. This will run on our model locally. We'll respond with a JSON response, and if we inspect that JSON response, we're going to see a key value pair here of predictions and a list of lists, and each one of them has the output for the appropriate input. So 9, 2 times 9, 18 minus 1 is 17, so we're very close to 17. And the other one was 10. 2 times 10 is 20, minus 1 is 19. 2x minus 1, and this is close to 19. So we see we got pretty close answers. The only difference is that the model was running under localhost 8501 port. And yeah, we can explore the prediction, the response text here, since this is just a JSON object at this point. So this was the newer part that we haven't seen before, as well as the setup, the installation, the configuration. So if you have any comments, questions, feedback, let me know, and I'm happy to answer them.
Can you scroll up a little bit? I want to see. So data is the X's, right, that you entered. That's
Yes.
that's what that is, right?
Yeah.
So the nine and the list of list, basically.
Yes. So we had our X's, which is 9 and 10, and then data was using this signature name, which was the serving default and the data itself. I want to show, if there are any more questions, how do we do this for a more complicated input and for a more complicated model? But the general pipeline is this, that you have a model, you export it into save model format, you configure your models, your server on a specific IP and a specific port, and then you just have to make sure that you format the data properly so that the model can read it. So this week had a second notebook. I'll briefly cover it. And here the only difference is instead of the dataset being that very simple, list of floats or numbers, now we have images. So I'll be using the fashion MNIST. If you remember this fashion MNIST dataset that has 10 categories, ankle boots, dress, bag, shoes, t-shirts, jeans, and so forth. We'll be using that as our dataset, and we'll train a model that basically, given an image, a 28 by 28 grayscale image, returns you which of these 10 categories or classes that image belongs to. So in terms of libraries, nothing new here. This is the dataset that I mentioned again. We'll be using TF Keras datasets are here. This is available under Keras.datasets as fashion MNIST. It's also available under TFDS as well, which you've seen in the past. And under there, under load data, we'll get a tuple of training images. There's a little bit more. And training labels, as well as test images and test labels. These have values between 0 and 255 in terms of pixel intensity. We'll normalize them between 0 and 1, so our model sees normalized inputs. As well as just reshape them in this 28 by 28 by 21 by 1 format. And the class names. So this is the list of class names. So t-shirt, trouser, dress, coat, and so forth. So there's 60,000 28 by 28 by 1. There's only one channel here, grayscale image for training purposes and 10K for testing purposes. This is an image, so we're going to use slightly different sequential model here. We're going to use a CNN, a convolutional neural network, a 2D CNN. Our input will be 28 by 28 by 1. We'll be using 8 filters or kernels here. Their size would be 3 by 3. Stride, activation, name, and so forth. We've seen this in the past. Right after that, we'll just flatten the output of this convolutional neural network. We'll pass it to a dense neural network. Our classification. This classification task has 10 classes. That's why we have 10 units here with softmax activation. And looking at our model summary here, we see most of our parameters are in this dense layer, simply because after flattening it, we have so many weights and biases coming in. We'll train a model for 5 epochs. Adam as the optimizer. This is a classification task, so we'll be using this sparse categorical cross entropy loss function. We'll be monitoring accuracy as well as we train. And then we have our training images, we have our training labels, 5 epochs. Let's train it. So you'll see here we're training it for 5 epochs. And this is the training accuracy and loss. And then in the end, we can do a model.evaluate on the test images and test labels to see how we are doing on the test data set. Kind of using test data set as validation here, almost, which is 87%. So decent, we want decent performance here. Similar approach here to saving our model. The model is the one that we had above. The path is, again, the temporary file, temporary path under our host. So we're saving it under the saved model.pb, and all the weights and biases are under this variables folder. If we explore it with this saved model CLI, we need this serving default, which usually doesn't change. And here we can see what is the input, right? So the first one is a 28 by 28 by 1 shape. And the output is just a list of 10 numbers, which is basically our probabilities of what is, what image are we looking at, and what is the probability that it's one of each category. Scroll down a little bit here. We saw this before, installing TensorFlow model server, or downloading it, installing it, and then running it in the background. Is exactly the same as before. Tailing the logs, making sure it's up and running. That's exactly the same. We can, these are images, right? So we can print them. So this is just an example, a random image here. This is a shirt. And now what we're going to do is we're going to take from our test images data set, we're going to take the first 3 images, and we're going to convert them to a list. So basically, we're going to flatten an image as it is, as a 28 by 28. We're going to make it as one long list of 784 elements. So there's 3 of them. And if you want to look at the data, how it looks, most of them will be 0 in the background, and some of them will be some values higher here in the middle. How do we make the request? The request is exactly the same here. It's an application JSON header. The local host is the same. V1 models. We named our model differently here. It's a fashion model. We'll be using the predict method. The data that has the signature as well as our collection of images, and the header that is right here.
George,
Yep.
He says right there that like they're gonna ask the server to give us the latest and not specify a particular version. But doesn't he specify it when he says V1?
Yeah, he specified. Yeah, I was thrown off by that as well.
Okay,
yeah.
okay.
No, I haven't tried it without a V1. Maybe I can try it without a V1 and see. But yeah, I think what Lawrence was saying, that if you don't specify it, you can basically let the model give you the highest version by default, which is a nice feature. Some other APIs usually follow, like instead of V1, they do latest. But yeah, I'll try it without any version and see if I get a valid response. Cool. So if we do that, we're going to get, again, we're not getting an image back. This is just a visualization of what we're getting, but we're getting a prediction 0, and we're getting a list of 10 numbers. So we're going to take the argmax of those to see what class the model predicted, as well as what is the actual label here. not sure if this is right, because to me this looks exactly the same. So I need to take a closer look here. But the goal is basically we know the test data set has labels as well. It's almost like a validation set, I would say. So we know what our model returned. We know what the true value is. We want to make sure, we want to compare those basically. I think we tried here with another version. Let me see. Versions 1. There you go. So I think the version is here then. That's my misunderstanding. I thought the version would be here. But if you see here under fashion model versions/1, this is running version 1 versus here, it's just running fashion model, no version.
Yeah, that makes sense. Do you have any idea why there's a V1 there after the?
Yeah, that's a good one. I don't know. I thought this was a version number, but yeah.
It's not obvious. Yeah.
It's not really. Yeah.
Okay.
So then we pass it 3. Let's see. These are the 3 images that we passed. So this was a pullover. So we predicted it correctly. This was a trouser as well. Predict that correctly as well. Okay. So apart from this version and this class names, yeah, I think this makes sense to me. I'll clarify here. I'll follow up and look it up a little bit more in detail. This V1 versus versions 1. But this was interesting because basically you're treating now images, right, as NumPy array, which you can. We've done that in the past, and serving them now, providing them as input to this remote server. Let the remote server do the prediction and give you a list of 10 items. You just pick the max, and you try to figure out based on the index of that max value what class it belongs to, what class it is. Cool. That's all I had for TensorFlow Extended. Oh yeah, let me see if I can show you here.
Down.
So if you remember, let me spell this off here. Okay. We saw very few, like the beginning part of an image, but if you plot or if you show the entire 784 pixels of a 28 by 28 by 1 image, it's going to look like this. So 0 meaning there's no content there, it's just dark. And then somewhere here we have some values, right? This could be a bag, a trouser, I don't know, based on the values. So this is what we're actually sending to the model. This is the instances part of it. So we're sending 3 large arrays with numbers between 0 and 1. Cool. I'll stop sharing here and open it up for comments or questions.
I just thought it might be interesting if you were to, one of the models, whichever one's easier, put in incorrect data. As the consumer, you give it the wrong data. What kind of error message do you see back from the API?
Right. That's a good one. Yep. Meaning, like let's say, like instead of numbers, strings, or like unexpected.
Anything, or even that version number. If you gave it the wrong, version equals 2, or it could be the data, or the URL call could be wrong. I'm just wondering what the errors look like.
Got it. Yep, that's a good one. I can try that.
I mean, I assume you still get a response, the same kind of response, but it must have some error format inside of it.
Yeah, I can try it in the end if we have time.
That's
very easy. I'll just run the notebook again.
Okay.
I got a quick question, George. So in the examples that you just ran, the TensorFlow serving, I presume everything was running on the same sort of machine, like the TensorFlow serving was running on the same machine as like the inference engine. Like, I mean, I thought like from the earlier part of the kind of overview that you gave, it looked like that the idea behind TensorFlow serving is that you could, have it serve as an intermediary and serve models and data to other types of machines, whether it's a edge device or is it an easy extension to just have this run on another? I guess you give it a URL, and everything. It's easy to just have it run somewhere else.
Yeah. So I mean, the course followed this path because it was simpler to open a Colab notebook and use that as both a training environment as well as the serving environment. But yeah, you're right. In a real production environment, you would have completely different hosts. So probably have like a very heavyweight environment for your server, and then your applications could be anywhere. It could be, again, an app. It could be a web app. It could be anything, and it's just making HTTP calls.
So if there's some kind of translation, like you kind of earlier alluded to that, like one deployment environment could be like a TensorFlow Lite, and another one could be a JavaScript. And so is there some, maybe this is a later part of the lesson or whatever, but how would you have it handle heterogeneous kind of environments like that? Do you have multiple models? Okay, yeah, this one right here.
Yeah, this pusher here, right?
Pusher, yeah. So you were just pushing onto, which one were you pushing onto?
I was pushing on this TensorFlow serving. I was pushing basically on, like, I want to call this maybe like the cloud or desktop version of it. That's how I would describe it. The other ones are if you want to push your model to specific edge devices like Lite.js, or if you want to put your model on a repository or collection of models that Robert will describe under Hub. But for me, this is the beefed up version of JS and Lite. This is basically, okay, I want to push this on a central location, which has, all the newest and fanciest GPUs, and I can centrally upgrade it. I can centrally monitor it. I have full control over it, basically.
Yep.
So this is this paradigm. It's completely different than the other ones. The other ones is you train somewhere, and then you save it in a format that is appropriate for your edge device, and then you push it. But then the model is kind of on its own, right? Like you say you push version 1 under Lite and JS, tomorrow you're going to have version 2. You need to push it again. Mm-hmm. This is more like, let me handle all the requests centrally and serve them.
Okay.
That's the difference.
Thanks.
Yeah. Cool. So I'll try and break it in the end and see how it behaves.
Thanks, George.
Thank you.
All right, I guess we'll shift our focus to transfer learning. You want to take it away, Robert?
I guess it's time to talk about the hub.
Yeah, the hub.
Okay, welcome everyone. We're gonna move on to week 2 of course 4 of this TensorFlow Data and Deployment Specialization, like David introduced in the beginning. So this is the last course out of the 4, and it covers a variety of topics. I get the impression there's not going to be a ton of relation from one week to the next. It's kind of just a real basic intro to some topics that once you've been using TensorFlow for a while, you kind of want to learn a little bit about. So without further ado, I'll share my screen. And let's see. Let's go to this one. And I'll move this down so I can see the tabs. So this week here, TensorFlow Hub, there are a handful of units. They go through kind of an introductory bit, just an introduction to what TensorFlow Hub is about, why you would use it, basic use cases, concludes with a Colab notebook on a very basic example. And then some more specific use cases. There's a unit on text-based modeling where we'll go through an IMDb review problem where we're going to pull a pre-trained word embedding model off of the TensorFlow Hub. And image classification, we will do the same with a model that has been trained on ImageNet. And at the end of the week, there was, as usual, there's a quiz and a programming assignment. We won't go through those. We'll focus on the material from the course. So I'm going to start just by letting Andrew, I think Andrew is the one that speaks in this clip, just introduce the ideas from this week in his own words.
In this week, you will learn about TensorFlow Hub. One of the coolest things about working in deep learning is the ability to download someone else's pre-trained model that they've open sourced and be able to build on top of that. You may have heard of tools like Model Zoos, or you may have downloaded models from GitHub and mess with it to get into your own framework. TensorFlow Hub makes all this much easier.
And that's the vision, is to make it as easy as possible. So models are stored in the repository, they have an endpoint URL, and then there's a couple of lines of code that you can use to point to that endpoint, download the model.
And we'll skip to the end of this little video.
Quickly. So in order to do this, you need one line of code to download the model and one line of code to point to the layers to train. Why do we need so many videos to teach people 2 lines of code?
We want to be detailed. That's a really good point there.
Maybe we'll make it 1 line of code someday.
That's what we're working on. Next version.
TensorFlow Hub should make downloading pre-trained models and getting going on new projects much faster. So let's go learn about it in the next video.
So I have to admit that they do show us more than 2 lines of code. There's quite a few lines of code here and there. But let me jump into some visuals from the course and give a high-level overview. Any questions before we get started?
How long do you think it'll take you to cover 2 lines of code?
Well, let's see. It's 7:55 now. We'll find out.
It's more than 2 lines.
So I've grabbed a few visuals from the course as usual. This is from the same one that George showed earlier, just showing where this all fits into the TensorFlow and TensorFlow extended ecosystems. The TensorFlow Hub, you can view it as part of the pusher, but really more than those other 3 modules or parts of TensorFlow extended, this one is more used for people to pull information from rather than to push it to. Some people do push to the TensorFlow Hub, obviously, or otherwise there wouldn't be models there. But let's go to the other view that we get from the course here about where the hub fits into TensorFlow and TensorFlow extended. So typically when we talk about training a model, there are, I would say, 4 ingredients to the recipe of training a model. You need a model design, you need data to train the model to, and then you need to define what makes a model good versus not good, and that we know as the loss function. And then you have to tell the model how it's going to get to a point that is good, and that is the optimizer. And once you choose a data set, model design, loss function, and optimization function, at that point it's just executing the process to produce a model that can hopefully generalize well to new examples. So what they're showing here is that you might be able to design your model in Keras, like we've done dating back to the TensorFlow in Practice course, specialization, that we covered last year during 2020. And all the videos from that are on YouTube as well. And you might be able to pull a data set from TF datasets, which we discussed in detail how one might design a pipeline for that back in course 3 of this specialization last month. And then once you have these things and you've picked your loss function and optimizer, which is usually part of the model design, the architecture is the other part of model design, you will go to train it, and you might want to train on a CPU, GPU, TPU, there's any number of options. And you might analyze that training with TensorBoard, which I believe David will talk about next week as part of week 3 of this course 4. And then we have, often you're going to want to produce the resultant model in a saved model format. And saved model is this standard TensorFlow format that George introduced us to during the week 1 portion of this talk. And at that point, you may or may not choose to push your model to the hub. If you can push it to the hub, or you might choose to deploy it to TensorFlow Serving, TensorFlow Lite, or TensorFlow.js. I suppose the reason for putting this in present mode is that you can actually just step down with one click. There we go. So why use TF Hub? What does it offer that you can't do with designing models yourself in Keras? There's a number of reasons that, and Andrew was alluding to this with his very first statement, and this is the idea that if you build on other people's work, in deep learning, we're just constantly building upon the work of others, and the vast majority of what anyone publishes is 99% built on what someone else has done, and they've added the 1% to take it to a new level, solve a new problem, etc. So by transfer learning, you may be able to start at a model that works reasonably well already, and you can get a certain level of performance, you increase that performance, needing less data of your own, needing less training time of your own, you can speed that up, and possibly by leveraging all this extra data, you can improve generalization. And this can be super important when we're talking about such big data problems as many of the major tasks these days in video image classification, in text classification, text language models. There's so much that can be learned by having seen an enormous corpus, and the only way that you can really leverage that data and that knowledge that has been learned elsewhere is to piggyback on a model that has already been trained. So by doing so, you take less training time of your own. In many cases, it makes things feasible that you could never do on your own. A lot of the state-of-the-art models, of course, have been trained for hundreds of TPU hours, if not thousands of GPU hours in some cases. And you can not only speed up your training, but you can also improve the performance because you've just given it far more data than you could have ever given it yourself. So what might you find available on TensorFlow Hub? There are a number of organizations and even some individuals that have published to TensorFlow Hub. These are some examples. Google, of course, has produced a lot of the models on there. DeepMind, I think, has uploaded a bunch of stuff to TensorFlow Hub. That's this icon here. And TensorFlow itself, I guess they're counted as separate from Google for some reason. And then there's a lot of other models that you can find up there as well. let's see. Yeah, I think the problem domains is the next bit that I wanted to talk about. So we have text, image, and video are probably the three most commonly used problem domains. And the most common use case for text for transfer learning is to pull word embeddings. A lot of times language models and other NLP models, the major value that they may provide to a different task other than the one in which they were trained is ready-made word embeddings, which are, as we've covered in some previous courses, these are feature vectors essentially of words. You can have sentence embeddings. We'll see a little bit more later in this course. There are a number of problem domains within images, classification, object detection, image segmentation. You can generate new images, style transfer, etc. So here are your 2 lines of code. Do you think that this is going to solve all of our problems in these 2 lines of code? We just see here how to install TensorFlow Hub and how to import it, but we of course need to actually use it in future lines of code. So typically, as I think Lawrence was mentioning there, the 2 lines of code that he's actually referring to are one line to identify the location of a model that you want to pull off a TF Hub. In this case, you're just pointing to a URL, tfhub.dev, and the publisher of the model, the name of the model, MobileNet v2, and some other, which MobileNet v2 model it is, its classification, and its version 4. And then we're going to just load the module into this module object. And the really neat thing here is that this enables you to skip all of the steps with building a model in Keras that we have gone through for previous projects. And all we have to do here, once we've written these 2 lines of code to download this model off of TensorFlow Hub, is feed in a new batch of images, and we can immediately run inference from this model that has been taken directly from TensorFlow Hub. So this one was MobileNet v2, and MobileNet v2, let me show, let's see, I'll show more generally the website, but we'll first of all start with MobileNet v2, which is the one that we're looking at there. For every model that you can find on TensorFlow Hub, there's a documentation page such as this, and this one will tell you that this model is ImageNet classification with MobileNet 2. So this was the, what is it, ImageNet large scale visual recognition challenge, I think, from 2012. And it was trained on ImageNet, which is a very common standard data set for image classification. And there are 1,000 predefined classes in ImageNet. So by implementing this model directly off of TF Hub, in this case, what we're going to do is we're going to get those same 1,000 classes. So whatever classes MobileNet v2 was trained on, we're going to be able to predict this image here, and it's just going to choose whatever it thinks is the highest probability of those 1,000 classes. And in this case, it seems like it's doing reasonably well to identify it as a dog, although maybe these breeds are, let's see, we have Labrador Retriever, first of all, probability 0.58. That seems pretty reasonable. This dog looks a little smaller than that. And then there's some other Couvage. I didn't have any idea what that word is, but that is apparently a dog, as is a Great Pyrenees. So this is the result that you can get directly from applying this MobileNet v2 classification model directly off of TF Hub. In this case, 4 lines of code, including loading in your own images or batch of image. Let's see. So that's not all that you can do with TF Hub, of course. We also have the ability to take an existing module and maybe you want to put a different classification head on it. So in this case, you can actually build a Keras model and just throw this in as the first argument. Now in this case, all they're doing is putting an activation on it. So it's really just showing you how to build a Keras model that is replicating the same functionality that we just saw here. But by taking advantage of this tf.keras.sequential method, we can put it in as one layer of a list, and if we want, we can build other layers beyond that. So in this case though, with the full model, we're getting through module handle, we've already got the classification head on it. So another cool thing that TensorFlow Hub offers is an ability to download feature vectors directly from these same models. So that's what we see here. It's actually a different URL, tensorflowhub.dev. We've got MobileNet v2 again, but now we're getting a feature vector. And really that's just the lower layers of the same model, cutting off at a certain point. And we're going to pull in this module handle now. And now we can attach our own dense layer on top of it with the number of classes. And now the output size, I think, is 1280. So that is not the number of classes that we're going to need for ImageNet, but we can convert that to the number of classes that we need with this dense layer and activate softmax in the same way. One thing that they point out in the course is that these modules come without the top layer always comes without an activation, which is why we had to put an activation in this one. Another thing to note here is that in contrast to the one that we saw with the feature vector, here we have 1001 output size, which is the 1000 classes from ImageNet, I believe, plus a background class, which is the probability that the object is just something that's not in ImageNet. Any questions on the general stuff that we've covered so far?
So just to clarify the previous slide, you're basically recreating MobileNet, right? You're not changing anything.
That's correct.
And then the second option, you're just treating your MobileNet as basically a feature detector, and you can add anything you want on top of it.
Mm-hmm.
Perfect.
You could add one dense layer like is done here. You could add multiple layers.
Mm-hmm.
Mm-hmm.
Cool.
So when we run this hub.load command, what's actually going on behind the scenes is that the module is getting downloaded and stored either on your cloud system or on your local system. And there's a default directory. It looks in your root folder for the TMP folder, and then it will create its own subdirectory tfhub_modules if that doesn't already exist. And it will simply start writing signatures of models into that directory, and you get this saved model.pb along with any other assets. The assets folder, I think, will contain things like what are the label names for the classes that the model outputs. One thing that you can do is you can choose to store modules elsewhere. So you can relocate, you choose your own directory. In this case, typically you're going to need to define it as an environment variable in order to export it to a directory of your own choice. So you can import OS and set os.environ, key tfhub cacher to something else and export there. And then if you, from then on, your tfhub modules will automatically save in this other directory when you run hub.load. So that is the introductory material for this week. There are 3 Colab notebooks provided, and I just want to present those very quickly in detail. Then we'll have covered the material from week 1 or week 2. Any other questions before we go on to this?
Nope.
I think we're good.
Awesome. All right, so let me see if I have an active session here. So getting started with TensorFlow Hub, this one is the basic example that was presented. A lot of this example was already shown in the slides, but here we'll see the full version. Let's see. Can you read the screen here?
Yes.
You can close the table of contents if you want a little bit extra space. Or it's up to you.
Sure.
A little X there.
Close it entirely, or do you want to?
Yeah, you can close it.
Okay.
Thank you.
So a handful of imports. Import TensorFlow as TF. Import TensorFlow Hub as Hub. When you're running on Colab, it's already been installed, so you don't need to worry about the pip install bit. And here we're using TensorFlow version 2.5. And first of all, we're just going to look at that same image of a puppy that we saw earlier. And that's from Pixabay, which has a lot of free CC licensed images that are free and available for the public to use. And we can use the imshow method in matplotlib pyplot to show the original image here and show the pixels as the axes. And we can define a few methods to reformat the image. One thing that's worth noting here about using pre-trained models, pre-existing models, anything off of TensorFlow Hub, is that often the model itself is the easiest part in the process. What you're left to do is tie up the loose ends. So you need to figure out how to make your input data compatible with the format of the model that you're going to put it into. And you need to figure out how to take the outputs that the model will give you and make them suitable for your own task or your own application. And in many cases, when using models and taking advantage and leveraging the models available on TensorFlow Hub, these are the most difficult parts of the process. You also have a lot of choices, so you'll need to choose carefully between different types of models that may do the same thing. There's a lot of image classification models, object detection, but in many cases, it's just figuring out how to format your images and how to format your outputs that is a large part of the remaining work. So in this case, we're looking at an image that was 960 by 640, and our model requires the image to be 224 by 224. So we're gonna have to take this dog and make it a lot smaller. So we're going to resize it. We can just resize it directly there. That's what they do in the example. And it's going to change the aspect ratio a bit. Now it gets a little skinny, but still quite recognizably the same image as before. And we've plotted it again here with the new image size showing 224 by 224 by 3. Since we're going to be training it and producing an ImageNet prediction for it, we'll get all the labels for the 1001 classes. And in this case, we're just going to pull them directly off of Google APIs. ImageNet labels.txt is a file there. And there's a total of 1001 labels representing 1001 classes. So we can look at the first 5 labels. And the background label, the non-ImageNet object, is the first one. And then immediately thereafter, they jump into tench, goldfish, great white shark, and tiger shark. I'm somewhat curious as to how the tench managed to get the coveted top space on the speed dial here. It's a fish that I had never actually heard of, but I guess it's native mostly to Central and Eastern Europe and Russia, I gather, freshwater fish.
Now you know where the developers are from.
I guess that's so.
Is that what it is? Cool.
So some other 3 fish here that are a little bit more familiar, at least to those of us in the Western Hemisphere. So loading a TensorFlow Hub module. So as we described earlier, all you need to do is just find where the location of this module is. And so in this case, we have the module is located here. And when we finish this notebook, we'll go into a little bit more detail and look around the TF Hub site, because there's a lot of other models that you can browse there as well. And I didn't go through that as part of the intro. And then again, we have our hub.load module handle. And now we have the module, and we can immediately run predictions on it. Predictions equals TF. We just need this softmax function here that's in the tf.nn library. And that will give us our probability values for the top 5 classes. And we get again, the top 3 here are Labrador Retriever, Great Pyrenees, Couvage are the top 3. And then somehow we get a tennis ball. That's, I guess we're seeing the round shaped face, and I don't know, a little bit of a stretch, but maybe not the worst.
I think it's the green in the background, maybe the grass.
Or the collar there. The collar, see his collar?
Uh-huh. Does the collar look like the seam of the ball?
Yeah, it's kind of round and yellow.
Huh.
I think it's the grass.
Yeah, it could be the green background there is
It's a stretch.
probably behind a tennis ball. I don't know. And then I think the 5th one was another dog. What was that? Oh yeah, Old English sheepdog.
Maybe somebody's playing tennis in front of the puppy, and there's a reflection of a tennis ball on his eyes that we don't see.
Like CIA enhanced.
Right? And CIA super resolution analyzing, zoom in a little bit.
Or maybe it turns out that this is actually, unbeknownst to me, Roger Federer's dog.
That would make it a pretty good model then, if it captured that bit of detail.
Yes, we are giving MobileNet a lot of credit here. So using a TensorFlow Hub module with Keras, this is the second use case that we talked about earlier, where we have a sequential. Now we take the module handle, and instead of just using that immediately to produce predictions, we can build it as part of a Keras model and throw an activation on top of it, and you get the same model back and perform inference with that. And we can see that we're getting the exact same predictions values that we had earlier using the Keras version of the same model. And the third use case, we can use complete models as we did in the previous section, but maybe the most compelling use case for TensorFlow Hub is that it enables us to take advantage of transfer learning with these feature vectors where we can put our own classification head on top. So a feature vector here, we take the module handle to be this feature vector 4, and now we can give it a completely new classification task with 20 classes and build a model. And at this point, we don't actually run this model. We haven't even defined what the classes are going to be. We say num classes, but we haven't told it what the 20 classes actually are. And here there's just a little description of how one will convert a TensorFlow Hub module object into a saved model, the format that George was describing for us earlier. A few lines of code here where you're just basically making a directory for this saved model and then untarring the compressed model object and writing it to the saved model directory. And now we can run this module locally, just directly from the saved model. And this
just Robert, just a question here. I mean, we're actually running it locally all the time, right? It's just that we're now not having to go back to TensorFlow's their servers to get the model.
That is absolutely correct. Yes.
Is that right? Okay. Okay.
Thank you for the clarification. And then a use case that shows what we went through earlier with how you can change the download location of TensorFlow Hub. Nothing new. So what I do want to show, and we haven't looked at yet, is what the tfhub.dev website looks like.
Before we go there, so we're pulling either a model or a feature vector and we're running it locally. So that means that our infrastructure should support it, right? So if we're using like a large model, I don't know. So far, I've saw that you've only done inference, right? But if we wanted to continue training, like if we wanted to transfer learning, we want to make sure that we have the right infrastructure to support that. So if we have a model with millions of weights and biases, we need to make sure that we have the right infrastructure to do that. Like this, for example, this NLP models that are coming up now that are like almost like 2 billion parameters, right? So yes, you can go to TF Hub and download it, but I don't know if you're able to run on Colab. Like you need something more, powerful.
Yeah, I'm not that familiar with what are the limits of Colab.
Right.
Robert, were you gonna show the transfer learning, how the transfer learning is done in this flow with TF Hub?
Yeah, there's the third notebook here goes into that.
Okay.
I failed to preset a water bottle here, so I'm gonna take a 20-second break and do that.
Go for it. I remember, David, when you used Model Hub back in the days when we were doing our coding challenges, that was so cool. Like everybody, I mean, I was defining my own model from scratch, like a bunch of layers, a bunch of dropout, flat, and all that. And you're like, oh, let me just pull from TF Hub.
Yeah, I use TensorFlow Hub all the time for a lot of work.
Right. I'm like, yeah, that seems so easy and so cool.
Very useful. Yeah.
Yeah, so tfhub.dev, this can be browsed by a number of filters. You can search by problem domain. Let's go back to the other page where I think we'll get a problem domain, image, text, video, audio. You can click on any one of those. You get a number of choices here. You also get some suggestions of models over here. If you want to filter by model format, maybe you want to use a browser or an edge device, you can look for models specifically that are already TF-Lite format. And you can look for models compatible with the Coral device too for training for if you want to use an accelerator with an embedded device. I guess here you get MobileNet and YamNet, which is an audio ontology.
I like this, the mobile format filter. I mean, it's so cool. It's already optimized and quantized and everything.
Yeah.
I'm surprised they have TF1 as well.
What was that?
I was about to say, I'm surprised they have TF1 as well, but I don't see anything.
Yeah, apparently there's nothing there anymore.
Okay.
You can filter by various publishers. This is interesting too. You get to obviously Google 1,000 models, but then it turns out there's not all that many unique publishers, and even some individuals get up here near the top of the list. Like one person publishes 10 models. The Digital Epidemiology Lab at Switzerland, AgriPredict, one model. Another individual, one model.
Now I know our next programming challenge, our adventure.
The Danish Mycological Society.
Right. Put deep learning adventures in this list.
Yeah, it doesn't take too long to bubble up near the top of the list.
Right. Yeah, cool.
You can search by architecture. I think we've already got a filter on. Let's see. Yeah, so you have language model like BERT, a bunch of GANs,
Nice.
CNN, ConvNet, deep lab models, bunch of them, a bunch of efficient nets, another GAN, another image model here, faster RCNN, Inception, Mask RCNN, the mobile nets that we saw, ResNets. Those are always mostly convolutional models, image nets, or image classification detection.
I wanted to ask you, can you filter by, I think you can by data set, like what data set they're using? Like
yes, that's
Cocoa
down here. Let's see.
Oh, nice.
Oh, yeah. There's a data set called birds or bicycles.
We should use that.
Is that talking about bird scooters or birds?
Oh, yeah, you're right. Maybe it's the scooters.
They seem like they might be at least a little more challenging to distinguish from bicycles.
Yeah. Let's see, Coco, right? Coco is there. CFAR, good. Celebrity.
And there's a number. I mean, look, there's 61
Coco
models that have been trained on Coco 2017.
Is our body ImageNet here? Let's see.
Is what?
ImageNet should be here, right?
Should be.
ImageNet.
200.
Okay, and different versions of it.
Mm-hmm. But this is the main one. It's large scale visual recognition challenge, I think. Google News has a bunch of them too. We'll see those in the text section.
Nice.
Natural questions.
I see a lot of Wikipedia. Yeah.
Yep.
Mhm. Some in other languages as well, like Spanish.
Yeah, there's a language filter at the bottom as well.
Oh, nice.
You can.
Oh, cool.
I'm assuming these are mostly text models. I haven't looked at this.
Yeah.
Apparently Spanish didn't make the list. Huh.
I thought I saw
Unless
that.
it's listed under Espanol.
Yeah.
No, oh, there it is. Maybe they're not in alphabetical order.
Yeah.
So yeah, looks like translation data, multilingual.
16 languages. Text encoder. Or just an embedding layer? Is that what it is? You give it a sentence and it gives you just a vector, a representation of it?
That one is the
That one
universal
is,
tensor encoder. Yeah.
Text embedding.
All of
I'm
them.
guessing most of them are embeddings.
All of
There's
them.
one that's for question answering.
Oh, really? Oh, cool.
Yeah, I mean, you do have the full BERT set of models. There's quite a few actual, more than just embedding, but yeah.
Oh, you have full BERT with like in Spanish? You can do that?
There is a multilingual BERT model. I think they have it on there. I can't remember. I think they do have one.
Got it.
It's like 12 languages.
Nice.
Yeah, there's my favorite thing, the search. Yeah, it's that, if you go back up, it's that lab SC. Yeah, LA.
LABSC.
So where it's 109 languages.
Agnostic.
BERT. Yeah.
BERT sentence embedding model. Oh, so you add this before your BERT model? Is that what it is?
No, it's the full thing.
Oh, it's the full thing?
It's the model. It's already been trained on 109 languages.
And what is the, okay, what task can you do with it? Can you do like,
Everything that BERT was trained for.
oh, cool.
That's pretty cool.
Maybe in one of our adventures we go multilingual.
You would use it mainly to get the feature vectors, right? And then you would use it for whatever you're doing.
Right. What is the most popular task that BERT is used for? Is it for like prediction, like predicting the next word, or?
Generation is very good at, as Robert mentioned, like the squad and glue benchmarks. It does very well on those.
Mm-hmm.
Well, I think a lot of people just use the embeddings directly from it as well for other tasks.
Yep.
Question answering, maybe?
Yep.
And when you go to one of these pages, you get a model format, so you can get it as a TF saved model, I guess. This
Oh,
one.
nice. A breakdown of performance.
Also a decent amount of documentation on this site, which is pretty useful. Some of the models, you can see the version history and what was changed in each version. I think MobileNet, you get that.
Nice.
Yeah.
Oh, yeah. Version 4, okay.
Yeah, it's MobileNet v2, but it's version 4 of MobileNet v2. A little confusing.
Different patches they added or issues they found.
Yeah.
It's like a candy. This is like a candy store for us developers. Like, all right, what is available here? Oops. Updated version.
Yeah, so I want to go through the text example from the course. Lawrence presents 3 different types or 3 different embedding that you can find on TF Hub. And all three of them are Google News, and there's various sizes and data sets from Google News. You get the Google News 130 gigabyte corpus, and I think that's the smallest one. You get 7 billion words here. And this one, you get 200 billion words.
I think these are tokens, right? So yeah, so maybe like
yeah, I think you're right. I think they're
smaller
tokens.
parts of a word, right?
Mm.
Like syllabus or.
So just quickly to discuss what we had in the second notebook from the course. We have the text classification. We're going to look at the IMDb dataset. And that's this one, this Stanford IMDb reviews dataset. We have, I think, a test split, 25,000 reviews, train, 25,000. And each of these is essentially a long string of words, which is sentences that someone typed in for reviews. And the purpose of the task is to classify, is this a positive review or a negative review? And I think the labeling is just done based on how many stars the reviewer gave the movie. If it's 4 or 5 stars, it's rated positively, and 1 or 2, I think, is rated negatively. Let's close this other notebook here and run all on this one.
If you don't mind closing the table of contents, that'd be perfect. Thank you.
So again, here we just have our standard imports, hub, TFDS. We're downloading IMDb. I did want to point out this, we're splitting the data set a little differently than IMDb does, because we're going to want to use a training set, a validation set, and a test set, and the IMDb really only has train and test. So in this case, we're going to use the 60% of the training set for training, 40% of the training set for validation, and we're getting the splits using this syntax that we first covered in the pipelining course. So it takes a little bit. Eventually we'll get through and we'll explore the data, and we're just going to look at a few examples of the sentences that, and for training, we're just looking at the number of examples, and then we'll look at a few examples, I think, in a later. Yeah, 2 classes, 25 movie reviews is what we already went over, looking at the documentation page for the source. Negative and positive are the 2 classes. And we're just going to look at some examples. This was an absolutely terrible movie, don't be lured in, etc. I've been known to fall asleep. This is the kind of film for a snowy Sunday afternoon. And we get the negative, 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 positive as these first 4 labels. Now we want to get word embeddings, and this is where we're going to leverage the TF Hub. So we already identify our source for the embeddings. We'll use the GNews Swivel 20dim. That's the first one of these. This one right here. GNews Swivel 20dim. This one uses with OOV, and I think the one in the notebook is not using with OOV. The difference is whether or not the embedding includes a vector specifically representing the out-of-vocabulary token or not. And once you have the model, once you have the embedding defined as that, all you need to do is take hub Keras layer of that location, and you have a layer that you can then use as part of your pipeline. So we'll take a batch size of 512. We'll shuffle the data. Excuse me. Shuffle it, batch it, prefetch. Validation data will just be batched and prefetched. And here's the first batch of 512 sentences. At this point, then we're just going to take our layer, our embedding layer here from the hub, which is just like a feature vector. It's going to take a sentence as input, and it's going to return an embedding vector. And one of the real values that this provides for a text problem is that you no longer have to worry about so many of the details that are a challenge in text processing. Remember that text data may be coming in, but we need numbers in order to use a neural network. So back in the TensorFlow in Practice course, when we went through the neural networks, we had to come up with a way to, frequently we would tokenize the words, we had to do a variety of other processing, and eventually we would train an embedding.
I remember that was such a long process, right? And
yeah, and you have to make a number of decisions in the process.
Yeah.
Size of vocabulary, padding vectors that don't match a certain size.
Right.
In this case, all of that is taken care of for you by choosing a model from the hub. You just get the toss in a layer here, and you're going to be able to immediately convert your sentence inputs to vector outputs. One thing that they don't talk about here, but Lawrence did mention in the course, is that this model is producing sentence embeddings, not word embeddings. Sentence embedding is just a method for aggregating the word embeddings within a sentence. Often you might use the mean of the embedding vectors of the words, but there's any number of ways that one could generalize that to other functions if desired.
And Robert, is that embedding 20-dimensional? Is that why that 20dim is there, I assume? Okay.
That is correct.
Usually we work with much larger embedding size, like 32 or 64 or 128.
Yeah, I think he was saying that the minimum that you can sometimes get away with is about 8, but typical values can range up to the low thousands. From there, I think 100, 300 is very typical.
Wasn't there a rule he mentioned in the previous course, like the square root of something or the cube root of or was that for something else?
Was that for embeddings?
I think it was for embeddings. I'll look.
That was for embeddings. Yeah, I don't remember the rule off the top of my head, but yeah.
The cube root or of how many unique words you have. Because he had 100 and he came up with 8, I think.
Yeah, it was, but it was word embeddings, not sentence embeddings. So probably a different rule for this.
And there's so many unique sentences, right? Billions and billions. I mean, millions probably. Definitely, yeah. So many combinations.
So once you have your model defined, you take your hub layer, you put a couple of dense layers after it, just like we're treating this just like another layer, even though it's actually it could be a multi-layer neural network, or it could be just a single layer. In the case of a word embedding, it could be just a single layer.
If you do model.summary, I'm curious, will you see one layer or will you see multiple? I think only one.
It'll only show you the one. I can tell you that.
Okay.
Is that right?
Is it because it's a feature vector or is it a model? Or is this keras layer? Okay.
So it hides the details, right? I think in this case you can't take something off of the hub and pick it apart layer by layer. Is that true?
But I think you can, right? You can just focus on model dot keras layer, and it should give you everything, shouldn't it? Yeah, hit it. Or maybe it'll just give you the
No.
or layer 1, or maybe the layers. Yeah, 0. Dots. I don't know.
You can draw a dot summary, but it probably won't tell you much.
Variable, metrics, losses, weights. So you probably can get all the weights, but it's going to be a long list. Trainable weights.
Well, the weights that would certainly tell you what the layer structure is like.
It's cool.
If I did,
yeah, length maybe.
where'd that go? List. So it's probably one layer, right? Uninitialized variable.
Um,
Does that have a shape? There we go.
20,000.
Vocabulary size is 20,000, and the embedding dimension is 20.
Ooh, interesting. So you can kind of peek around, but yeah, I'm hoping maybe there's a way you can see the underlying architecture and structure. I don't know if you can.
Yeah, I mean, in this case, it's probably literally just a matrix multiplication.
Oh, wow. Yeah.
Because it's just an
Single
embedding.
layer. Yeah.
Yeah, just a big matrix multiplication. Got it.
Yeah, and without an activation, most likely. Yeah, it's basically a 20,001 is the number of rows, and each row is the embedding of one word.
Right. Or sentence. Yeah. It's like a lookup table, basically.
Yeah, it's a lookup table. That's the way word embedding vectors typically are constructed, right? Just a concatenation of row vectors,
Right.
or column vectors. Yeah. So we can take this and treat it just like a layer in a typical neural network. Compile it, fit it, and do our predictions. And in this case, we're just going to do a simple evaluation on the test batches, and we get a classification accuracy after, 20 epochs of 87%.
Wow. That is so cool. Look at your training accuracy. Like you reached 90 something, and look at your validation accuracy. Like performing pretty well. Yeah.
Yeah, they don't really start to diverge substantially until about here.
Mm. So was it okay? Did we use the same data set? Is that what we used? No, right? The model was trained on Google News, but our transfer learning task was on IMDb reviews, right?
Right, and keep in mind that the Google News is not doing any kind of classification of sentiment.
Right.
It's literally just giving you information about the language enough to construct the embeddings. It's just giving you the embeddings.
But when they construct the embeddings, they probably had a task behind the embedding, right? After the embedding. Or is it just pure embedding creation without a task? I don't know if you can do that.
And there's always some kind of task involved in generating an embedding,
Right.
whether it be a masked language model, something where you're just covering up a word and having the model predict the word.
Right. But it's so cool that because that task is completely different than our task. Our task is a binary classification task. But the task that the embedding was trained on could be something else, like you said, text generation or, I don't know, sentiment analysis, I don't know, whatever.
You can imagine it if you think of like a CNN model that's been pre-trained. It's learned to pick out basic fixtures like lines and vertical lines, circles, whatever, right, as features.
Mm-hmm.
And then you can feed it into your model and quickly learn how to use those basic features detector, right, to train your model. This is the same thing in the sense it's learned the basic aspect of the language in an embedding. And now you teach it how am I going to use those basic features of language to predict my classification rate.
Well, in image, it's easy to understand because usually you're trying to detect what's in an image. But yeah, in language, like depending on the task, you might get completely different internal embeddings. Like if you're doing mass language generation, or if you're doing classification, like I would imagine the features would be completely different. But I guess they're strong enough, that just by adding one extra layer, we can transfer learn on a completely different task.
Yeah, I guess you're looking at, if you think of it, you're looking at sentences and you're learning underlying features of those sentences, right? So you could see it learning on Google News, hey, this is associated with, it groups maybe bad sounding, negative sounding sentences together, sentences that have to do with airplane crashes are grouped together. Sentences that have to do with winning marathons are grouped together, right? It's learning that kind of understanding the language, and then when you apply it to us, well, it has those similar type of sentences which show up in movie reviews, right?
Yeah, let's say maybe the news one was what category of news is it? Sports, technology, finance, business, whatever. Versus here, it's positive, negative.
I don't know if they did that kind of classification. I think I suspect what Robert said, it's probably a mask where it learns how the sentences should be shaped and what words should go together. So it learns more basic level.
It's kind of an unsupervised task. It's not told to classify anything other than just to reproduce the text it's been given.
Right.
Interesting.
So there was one more collab notebook here I want to briefly touch on. Transfer learning with TensorFlow Hub. And that is, in many cases, the whole point. You can take one of these models and instead of getting the whole model, maybe you just want those lower layers that have learned how to detect edges and faces, and maybe you want to do a different task than the model was originally trained on. In the case of the language models, you may be taking a model that was trained to answer questions, and maybe in that case it generated embeddings, and you want to use those embeddings for a completely different task, such as the IMDb review binary classification. So how does one do transfer learning with TensorFlow Hub? Well, we saw the example earlier. I guess I should cut out of this collab here, and we'll try to start this one.
Is this another example of transfer learning? I thought we did transfer learning before, but it was with text, right? That's the difference?
Yeah, I guess technically that was transfer learning as well. The The difference here is this one's going to be images,
Okay.
and it's actually using a full model, multi-layer model, not just an embedding.
Nice.
I guess an embedding is the most trivial example of transfer learning, if you will, because it's just a single matrix that someone has already trained for you. Whereas in this case, we'll be using MobileNet, so you're getting an entire convolutional neural network that's been trained, the lower layers for you.
Nice.
Let's run all on this one.
Mhm.
This is going to be pretty similar to the first image processing one. Here we're looking at cats versus dogs. Have we seen this data set before? Training set, validation set, test set. In this case, there is no validation or test split, so we're just going to generate them all from the training set. 80%, 10%, 10%, the same syntax that we did during the pipelining course. And they're going to show that the data set has X number of examples in the train, and I think it's 2,000 here because there's 2,500 in the original, and you're getting 80% of them for the training set. And then, oh no, I'm sorry, 20. Data set has a total of 23,000 images. Okay, so there were 25,000 plus, I guess. There's multiple versions of this cats and dogs data set, right? Some of them are condensed. This must be the full one. Just two labels, cat, dog. Here's an example of a dog. Label is 1, means it's a dog. And we can take a image model from TensorFlow Hub. In this case, we get one of these selectors here. We can choose MobileNet v2 or Inception v3. So the default choice for the notebook is MobileNet v2, so we've already run that. Batch size is going to be 32. Once again, we're going to have to resize our images. We're going to have to resize it to a new size, image size, which I assume we defined earlier. That must have been in this, it's in one of these cells. Image size is a constant defined somewhere in this notebook. Batch size is 32. And of course we have to normalize it so that it appears between 0 and 1 as well, as you're converting from an unsigned 8-bit integer to a 0 to 1 float. And we run the model summary again. We're just going to get the Keras layer showing. So we have this entire convolutional neural network, but now it's being represented as a feature vector, which is just basically a function that's taking your input 224 by 224 by 3 image and converting it to a 1280 by 1 vector. And that vector is determined by the model that you've downloaded from TensorFlow Hub. Number of parameters here is 22 or 2.2 million, but these are not going to be trainable. And the trainable parameters is just this last dense layer. However, we could do fine-tuning. And if you do fine-tuning, then it does allow the other ones to change, I believe. Or, no, in this case, it's not selected. Just a single epoch, and we get 99% accuracy. We could turn on the fine-tuning bit, so that'll take a little bit longer.
How is that flag affecting your training? Can you expand it? Maybe there's something else going on there.
So in the Keras layer, there's a.
Oh, there you go. Trainable. There you go. It was
Yeah.
high. Yeah, I wasn't sure Okay.
Yeah, so what it's doing is it's making this, the weights in this can be adjusted now.
And you don't have to do it by that method. You can define it in where you defined your keras layer up there. One of the parameters you can put in there is, where you define the feature extractor, which is a keras layer. Where is it? Yeah.
Probably in this
Yeah,
one.
they do it in there. Yeah.
That's where the image size was too.
Yeah, I don't like
Yeah.
the hidden cells of code.
Right. So there where it says feature extractor equals hub keras layer, there's a trainable equals false by default, and you could set it to true if you wanted.
In the very end.
But they didn't do
Right,
it there.
right
They did it.
inside this function.
Yeah, they just took the default. But you can put it in there as trainable equals true. So you don't have to do it like they did programmatically.
So I think in this case you get a little bit. I think the accuracy actually dropped here when we fine tune it. It was a little over 99%, if I recall correctly, and now it's 98 point something.
So one thing they always say when you're doing like fine tuning is to put in that kind of functional learning rate thing where it starts with a tiny learning rate and then kind of the model warms up and you increase the learning rate and then you go back down again. It's that
yeah, I think that's kind of what they're doing very crudely right here.
Yeah, and the other thing is, do you train all the layers? No, right? You freeze like 80% of them and you unfreeze the bottom 20%.
You only have that when you have access to all the layers. Here you don't have it. That's not an option. Yeah.
Is it because why? I thought we were downloading the full model here, no? We're downloading
because the keras layer is a single layer, right? So you either train it or you don't train it.
Can you? Okay. If I wanted to do that, what do I have to do? Do I have to download the model?
Yeah.
That's not on TF Hub?
I have not been successful doing that. But.
Right. So it's either everything or nothing.
The advantage of what you're talking about is if you have a really large model,
yeah,
you may not have the resources, compute power, memory to train. Even at fine tuning, you may not have the ability to train all the layers, but you could maybe do, the very end of that keras layer. Yeah.
Exactly.
Yeah.
Or is it just like keep it as it is and I just add my own DNN on top of it and I treat that as my fine tuning?
Well, that's what you do. That's what he did when he didn't have this trainable. Right. So if you have trainable equals false, then that's what you're doing by default.
I'm just trying to figure out what is the trade-off of you adding your DNN and training that versus that, and in addition training maybe the last few layers of a large model.
Yeah, typically on difficult, large problems, you'll do what you said. You'll train your DNN that you attached at the end, but to get the best results, you want to do some fine tuning on the transfer model also.
I see. If you want to go the extra mile, okay, that's what I was thinking, right?
Yeah, because your data set is unique, right, compared to what the model was trained on. So there will be some differences that it can learn.
Right. It's almost like a temperature, right? It's like hot in the very end because you're training it, and it's cold in the beginning. It's frozen, and then it depends how far you want to go to the left. Right. I mean, extremely you can train everything, but then you have to train billions and millions of parameters.
Right.
You might even overfit your data. Sorry, Robert.
No worries. That's all the content from this course.
Awesome.
For this week.
So I'm looking at this and I'm seeing this transfer learning. This approach is pretty similar to what you would just do normally in keras. Like it's not. I'm trying to figure out where TF Hub helps a lot, but I guess the earlier stages where you pull in the feature, the feature extractor, and having that sort of library of models to draw from, but then you still have to give it like the loss function and the optimizer and all, like it's not dumbing it down to the point to that, you know, you're still having to do the transfer learning kind of the same way you did before, it looks like.
If you are using,
like Andrew Ng made it sound like it was going to be so easy, you know, like, I mean, I guess compared to like.
Well, it is so easy if you're using the models completely off the shelf.
Yeah.
Right? That was just the 2 lines of code or whatever.
Mhm.
The first notebook that Robert showed was the easy one where there was no optimizing, there was no training. He just did predictions, right? I mean,
yeah, that definitely was easy.
Yeah.
Okay.
Yeah, I think that the design idea here, as Lawrence indicates in that intro video, is just to make it as easy for developers as possible. But I think what that really means is you're only going to be able to make it super easy for developers to do something directly out of the box.
Yeah. Okay.
As always, if you want things to be super customized, you're going to have to do a lot of the legwork yourself.
I was thinking that they could like take it a step further and have, and again, maybe this dumbs it down too much that you lose some flexibility. And but I mean, even for the transfer learning, having like it automatically kind of remember like the default, have a default optimizer and a default loss function and all that. And let's say you wanted to just give it a new set of categories, a new set of classes, you could just give it just that, you know, and your training data, and then push a button and it even does the transfer learning, like all the details of the transfer learning it could do automatically for you. But maybe that's too dumb. Maybe maybe it's not that push button, you know.
Well, that sounds a little bit like the second example then, where you're just putting a different head on it.
That's a little more straightforward. Yeah. Okay.
the other powerful thing is, you know, these models are trained on literally, some of them in the case it's almost billions of examples in the data sets they use. And then if you have your own data set you want to apply this to, and you only have 100 samples to train on, it'll actually, you know, if it's very similar, you'll get very good results.
Yeah.
So you don't have to have, you know, spend all that time collecting labeled data to train a model from scratch. You can use a much smaller data set, so that also is very useful.
For sure.
Yeah.
Yep.
Can I?
Go ahead.
Yeah, I was going to say, can I wrap up with some going back to my examples with the API calls and
Yeah, you're gonna break it.
Break it and see what we get. All right. Awesome. Thank you, Robert. So first of all, I didn't cover the structure here. I just wanted to show you when you create this temporary folder and when you save the model as a save model format under temp, and then the version number that you give 1, you get the save model.pp, and under variables, you're gonna get the variables.index and data, which is basically your weights and biases. In this case, there's only 2 variables for us because this is a linear model. And just as a reminder, this is the correct call of the API. You have headers, application JSON, and request.post is localhost, port number, a version 1 that we thought it was the version number, but apparently it's not. Models, model name, an implicit version number that's missing here, and the method predict. And the data was just 9 and 10, and this is the output of the model, 17 and 19. So this is, if I specify the version 1, I get this expected output. Specify version 2, not servable, not found for request, hello world 2. So it doesn't have a version 2. I don't specify any version, doesn't like it. And if I miss it completely, it will give me the latest one, I guess. Oh, sorry. Let me run this a little quick. Make sure I have the right data. There you go. I'll leave this as it was. Version 1, specific version. Versions? Is that versions? Is that what it is? Okay. Now, if I miss something, let's say instead of v1, I added v2, I get this not found HTML request. The other thing is I completely missed it. I get this 404 not found. And basically, my model doesn't. This API call is not accurate or valid. Then that's on the API call, and I can play with this around if you want me to. The other one is on the data side. Right now, the data is serving has this key value pair of signature name serving default, and instances are data or input. The one thing that I changed is instead of a list of lists, I just made it one list, and I get an error that in 0, which is our body here, or actually the entire list, is not a matrix, and instead it has shape of 2. So it expects a 1-by-1 list, I guess. And then some bias add somewhere in the across the model. I think it failed. The other thing I did was instead of this serving default, which is the signature of my model, I just put my name. And so signature name was not found in signature definition. The other thing is instead of numbers, I gave it a string. Keep everything else the same. Failed to process elements, invalid argument, JSON value. String is not of expected type float. So it was able to detect the data type. Yeah, I tried different things on the API and the data.
It's pretty cool.
Yeah.
So the error messages are kind of informative.
Right, yeah, instead of generic ones, yeah. The API, if the API is not correct, you're going to get generic 404, but on the data side, it looks like you're getting more fine-tuned results.
Very cool. Very cool.
Yeah. Cool. I'll stop sharing. You want to wrap us up, David? Thank you.
All right. Thanks so much to our presenters. Great job by both George and Robert. Next week, we're going to finish off course 4 of this specialization with week 3 and week 4. We're going to start off by looking at TensorBoard, which is a very, very useful method or tool for analyzing your models. And then in week 4, we're going to look at an issue with privacy, which has to do with the data privacy that our models use and keeping that information private. And that'll be covering federated learning, which is one of many approaches there are to that issue, but a very interesting topic. Look forward to seeing you. Thanks for joining us. And I'm going to go ahead and stop the recording if everybody else is okay with that.
Yeah. Fine.
Thanks, guys.
Thanks everyone for joining us online.